Well, in this second part, we go deep with encryption, optical encryption. So we will make some introduction in the field, describe the basic architecture to encode an image, the different steps leading to experimentally implement an encryption, that we will back to the photorefracting materials and speckles, and this is the final point, dynamic encryption. So, as a resume of the first part, we have characterized speckle patterns, and two speckle patterns usually are completely uncorrelated if you change any optical parameters which is used to generate it. We take profit of these properties, changing wavelength, pupil diameter, or the system itself to generate different speckle patterns and to use it to encode images. This is the idea of this second part. Well, here's some point that should be remarked. Encryption is a data transformation of an image in a way that might be impossible to recover such data without an adequate key, this adequate key that was employed in the encoding process. Decryption is, of course, the inverse process of encryption, and well, that is the faithful data recovery into a recognizable form. Well, we expected with this encryption method? Two things. It's important to encode information so that it's difficult to decode if the key is unknown, but it's easy to decode if the key is known. This is the practical point. Otherwise, it's not efficient, the process. Okay. Well, of course, we use the parallelism that is inherent to any optical processing system. The advantages that we will remark are the many degrees of freedom to codify the data in a safe way. In particularly, the information can be codified using the phase of the light, so encryption data cannot be copied using intensity-sensitive detector. This is equivalent of, well, when you register the hologram, you are registering the direction in which the light is incident on the storage measure, so you can reconstruct the complete wavefront afterward. This is the difference of when you store the phase of the light. Okay. Well, another properties, of course, are bidimensional. These optical systems. Each pixel in a digital approach corresponds to a complex value. Consequently, you need a complex number to fully represent it. And, for instance, by using a spatial light modulator, in which you can register the amplitude and the phase of the light. Well, usually these systems are more secure than digital methods. It's very hard to reproduce the phase of the light, and you can take profit of this point. Okay, so what we like to obtain? If we have an image, this is the encrypted version of it. If you have the right key, you retrieve it in the right way. But if you introduce some change in your key, you get but only noise. And this is also a speckle pattern of this. This is the encryption of this image, and this is a failed attempt to get it again, and also is a speckle pattern. Okay, this is the basic architecture to encrypt an image. You have the input that you like to encode, diffuser, that is a transmitter random scatter. You obtain a first Fourier transform of this input, and in the Fourier plane you insert your key mask, which is another random transparency with scattering. After a second Fourier transform, finally you get your encrypted image here. Note that phi2 is a random phase function, this one, uniformly distributed in the interval 0 to pi. So here what you get is white noise. Your speckle pattern is a white noise pattern. But you have encrypted your image. Anyway, we must take into account that this is a linear operation. So there are efficient attacks to retrieve this encoded image, well, if you have any strategy to do it. In the decryption stage, you have your image codified, encrypted. You travel back into your system a first Fourier transform that arrives onto, but take attention at this point. This is the conjugate version of the key mask. After a second Fourier transform, you get your original image. But if you don't have this conjugated version of your key mask, you are unable to obtain, to recover the input. And now we have a tool to get a conjugate version of a beam, that is four-way mixing. We have shown in the final part of the first talk. Well, so this was the same experimental arrangement that we have taught. Here is the object at the first random mask. This length produces a Fourier transform onto the key mask. This second length produces a second Fourier transform onto the storage medium, which is the photoreflective crystal, and you get there the encrypted image. So, the reference beam retroreflected by this mirror produces the conjugate beam of the speckle pattern that travel back through the system. You see, at this step, you get only noise, but after passing through the key mask, compensates exactly point to point the phases and you get your input. This is the experimental way to do it. Well, in the following, we will show some examples as how to avoid that with some efficiency strategy an intruder can recover your encoded image without authorization. Which is the simple way to do it? If you have a spectral pattern that can be an encrypted image, and you add a second spectral pattern, you get a new spectral pattern. And you can distinguish it from both that form the final spectral pattern. This is the key point. So, if you implement multiplexing, that means several encrypted images in the same medium, you avoid efficient attack to succeed in this way. So, which is multiplexing? You have an input, first lens, key mask, second lens, encrypted image. Second input, if you do the same, you get superposed with the first spectral pattern, the second one. In order to distinguish here, you must change some parameter of your system. So, this is equivalent to change the key mask, to change this mask. For instance, if you change the wavelength, you change the diameter of your system, you change the magnification of your spectral pattern, or any other parameter of your system, this is equivalent to have another key, and you retrieve your image perfectly in this way. This is the approach or the strategy of multiplexing. So, in the decryption step, you must tune your parameter in the way that was set when you encrypt the corresponding input, and you get the decrypted image in the readout step. This is the approach. Well, for instance, which parameters can we use? Wavelength, position of the key mask, polarization of the light, or the size of your pupil. Position of the key mask, the second mask. If you move, if you shift it, this is equivalent to get a new mask, because you change completely your spectral pattern. Change completely means that is completely uncorrelated with the previous one. And this is enough to store your encrypted image. So, this is a right decryption, and in this readout step, you fail in some parameters, so you get only noise. Why? We like to obtain our signals completely separated, not in this situation. If you maintain the parameters of your system without changes, when you recover in this case both outputs superposed, or as we say with crosstalk. We have to avoid this situation. Well, for instance, by shifting the key mask. By shifting few microns, you can obtain equivalent mask and encrypt several inputs. One input, the mask in position 1, encrypted. You shift your mask, second input, second encryption, and so on. In the retrieval, in the readout of your crystal, of course, you must position your mask exactly in the position that was previously set when you encrypt the determined input. In this case, you obtain the same input as an output, in this case, because you are in the decrypting step. Well, this represents this situation. This is the right response. If you fail in positioning your mask, you have, well, nothing, some information, but it's clear that only a right position recovers a correct output. So this establishes a criterion to, well, to define a parameter in order to encrypt an image. In case of visible light and transparent scatter, few microns are enough to shift the key mask in order to multiplex several inputs. These are shown in the same. These are different images that are stored by shifting the second mask in your system. Another possibility is to change the polarization of the reference of the beam, for instance, by plates that you can shift, or you can control the ellipsometry of your system in a controlled way. And you can use it to encrypt as well. Well, another possibility is to magnify the mask, the key mask itself. This approach is only valid in virtual optic or digital encryption, because if you have a real diffuser, you can enlarge or reduce it. But this is another possibility. And a change, for instance, in 2% in the scaling of your mask fails in recovering the input. Again, you define a parameter to obtain multiplexing. In this case, magnification of the key mask. Usually, you compare your output with your input with a mean square error parameter. Is rather adequate to define the quality of the decoded image of the decryption receptor. This point means that both the input and the decryption are identical. This point that they differ, and these are quite different. You get saturation. So if you change more than 2%, the decrypted image differs completely from the input one. Well, this is all the scheme as we have observed in a previous slide. We have to avoid this situation of crosstalk. Here, the magnification was less than 1%, so you recover your input image, but you can observe a second one in the same output. This is clearly noise, and this is the opposite, but you recover the second, but the first image appears as noise. We like to obtain something like this, completely clean, or as clean as possible. Well, another possibility is blocking out some part of the pupil of the second transforming lens in the 4F architecture to get multiplexed. And as you get uncorrelated speckle pattern each time you block a different part of your lens, you encrypt very well using this simple parameter. In the redout step, of course, there should be a correspondence between the blocking parts with the recovered image. This with this. Well, again, if you use, in this case, the complete pupil, you get all the output superimposed. And this is a wrong result. Well, as far as multiplexing is a good strategy to avoid efficiency attacks in encryption procedures, you can divide your input image as a puzzle, and from your image you get several parts, and you get also a multiplexing approach. This is the idea of this representation. This basket with fruits are divided in several parts as a puzzle. Then you encrypt each one, and finally you convey all together to recover the inputs. Well, we can say, well, but we can guess that here is a basket with fruit. It's right here. Well, but if you divide more and more, here it's difficult to guess that it's a fingerprint, I suppose. So you can divide as necessary to encrypt conveniently. Well, therefore, the main conclusion are: multiplexing increases security. It's not possible to determine the number of encrypted images because are uncorrelated speckle patterns. And second, it is not possible to determine which optical parameters were employed in each step, in each encrypted image. So these are the main conclusions that we obtain from multiplexing. There is another possibility, the same experimental arrangement as we have talked. But now we change the size of the pupil of the second lens. So we can encrypt one input, change the diameter, simply change the diameter, and encrypt the second one. Therefore, this is a very simple example, but it works. an intruder can recover this image, but in fact, your true image is this one that is obtained just tuning your pupil in another position. This is the subject known as undercover encryption, that you have a fake image and a true image. The intruder obtained the fake one, and in fact the true image is this. Well, there are several strategies, some with some complexity. Perhaps we can skip this point, but one of them that is very common is to use one encrypted image as the key max for the second image that you have to encrypt, and so on. Therefore, when the intruder gets the image, of course, always is a fake image, because it's impossible to think that the encrypted speckle pattern was used as a mask to encrypt the truth. Well, there are some weaknesses in this approach, that if the output, the encrypted, is polluted with some noise, well, the true image is very affected due to the noise, because it's a successive encryption process in this case. Okay, this is an example. The fake and the true one. Well, the same. Well, another possibility, of course, is more secure to encrypt with a face mask, a random face mask. But in some cases, it's convenient to use amplitude mask in the encryption process. So, for instance, you can use one amplitude mask and its complement to recover the fake and the true image, or if you use the plain aperture, you get the combination, which is difficult to guess, which is the two in all these output. Well, usually the amplitude images are quite complex, so it's really quite impossible to obtain the distribution of the mask amplitude. Well, let's talk a little about a second architecture that is known as joint transform correlator. In this case, in the 4F architecture, you need a reference pin in your system. This is your input, this is your output, the encrypted image, in order to store your pattern. In this case, the mask, the object, and the mask are in the input plane. So, the system is inherently holographic. So you don't need a reference pin outside. This is this approach. input plane with both mask, length, and Fourier transform plane. Here is your encrypted image. Well, where the crystal stores the encrypted one. Then, when you reconstruct, in this case, because it's a hologram, you use the reference beam, which is the mask itself, and you get the input. Reference, object to be encrypted, encryption. Readout process. Here is the encrypted image. This is this one. You read out and you get your decrypted image. You can multiplex also by rotating the aperture. One of these, the reference one. And also you can encrypt in this way. Another possibility, another parameter we have not used is the wavelength, lambda. So you can divide your input in basic colors in different channels, and you encrypt in a wavelength basis. So it's harder to see now. We'll keep this. Well, in fact, you need, I don't know if it's possible to see this image, you have to separate the colors, the wavelengths enough in order to avoid crosstalk between the input that you are encrypted in. If in this case, you need to separate 8 nanometers in order to get encrypted image without crosstalk. Well, these are results. Of course, if your mask, you fail with one of your masks in decrypting, you obtain noise corresponding to these colors. In this case, you fail with the green mask or the red mask and so on. This is the input and this is the decrypted output. Well, 3 wavelengths, well defined. Also, you cannot make lateral shifting by the mask in this second architecture. We have talked before in this point. Or a final approach is to have a 3D mask, which means having 2 key masks in 2 different planes. This is equivalent to a speckled speckles. You project a speckle pattern into another speckle pattern. You increase the security of your system in this way. Well, anyway, if you in multiplexing add a new image and add a new one, you are adding noise when you recover the correct image. So, you have to set your parameters at determined values, but anyway, the remaining non-decrypted inputs contribute as noise. This is the main weakness of this multiplexing approach. Hmm? How to avoid this? Hmm? Suppose that we like to encrypt a temporal sequences of frames of picture. That is a movie, directly a movie. How to do it? By conventional multiplexing, as was described, you add noise in each decrypted frame from all the remaining frames that are non-decrypted. So the strategy should change in this case. Well, the approach is like this. This is your input, the first mask, Fourier transform, the key mask in the Fourier plane, second Fourier transform, encrypted image. Onto the encrypted image, you modulate it with a low frequency grading, as the first part was described in our first talk. And you get a modulated speckle pattern. Second, frame to be encrypted. The same procedure, but now modulate with a different grading. Different means different k-vector, different pitch, and different orientation in your grading. Both. And so on. Finally, then you multiplex all together. Afterward, this procedure is done. You see the difference? Now, we are not using any parameters. We are not tuning parameter inside the encryption machine. Outside, you modulate with a grading and then multiplex. Afterward, in the decryption steps, you must filter out each part of your speckle pattern, because it's equivalent to be labeled. Now, each speckle pattern has associated a grading, so you can distinguish. But it's the price you have to pay to avoid the noise of multiplexing. This is the first time this was done, the final part of last year, that movie was encrypted. So we will see, it'll last only 3 seconds. We will see the decrypted version of the movie that was encrypted. Okay, this one. Second? Oh. Again. This is a wrong decryption, of course. Wrong decryption. And now we extend this approach to color movies. But the key point in this case is you can't store all your modulated frame in the same medium as with the photorefractive material, because now you have divided your color movie in your basic colors, for instance, the 3 channels, the conventional red, green, and blue, and then in the final part, in the decryption step, you must unavoidable synchronize the 3 channels at a time. to get the color movie reflected. So the key difference is that you, in this case, you need 3 different channels. So this represents the 3 different channels. Each one is a monochromatic movie, but you must combine them in the final step. Let's see. This wrong decryption. Right decrypted, wrong decrypted. Now, the key point is the extent of your movie. How many frames you can encrypt and decrypt. So this is the, actually we are working at this point, at this moment. And well, it's rather complex to face this point. But clearly, if you reduce the diameter of your pupil to include more and more frames in your frequency plane, you are reducing the frequency content of your input, or the frame you are encrypted in. So this should be evaluated, which is the complexity of your movie. In the final slide, we see this effect. We will see this, I don't know, balancing pair, this in 3 different extensions. And you will see that there is apparent deterioration as far as the number of frames increases. Because you have reduced the aperture of your pupil to include more frames in the frequency plane, and you and this is a problem if you have an input which are very rich in terms of spatial frequencies. Well, this is the effect of reducing your pupil. The size of the speckle increases. Then, look, this lasts more. I don't know if it's possible. This lasts more and is more noisy. In the same here. You see, the noise, this noise is not due to multiplexing. Here are not a multiplexing approach. But it's due to, because the number of frames have increased. So well, this is the present state of this research. Well, thank you.
Any questions?
Thank you.
I have a question.
Okay.
Do you know, are there any practical applications nowadays of this system?
No, this is very, very recent.
Very recent. And of the, I mean also the, not the movies, the images.
No, we have turned to the problem of multiplexing to this approach. In fact, this is an old approach. It's theta modulation. You change tuning your parameter to a theta modulation approach. But you avoid the problem of noise of the different frames. The publication is very recent. It's in March was, and there was a huge response in asking us about that. We have not the answer to this moment, how to proceed in a practical way. But the approach seems to be adequate.
Any other
Thank you.
questions? Okay, thank you very much.
So I just want to